So now we have talked about the expectation of a random variable. And again, as a reminder, the expectation of a random variable, you sum over all possible values it takes, and then you take the value and the probability of that value. Okay, so it's the average or mean value of that. But look at two random variables. So suppose x is a random variable that takes only the value, let's say 3. This is the only value it takes. So if you look at a random variable that takes only value 3, and the expected value, of course, for such a variable is nothing but 3, right? Now, imagine that you have another random variable, y, that takes the possible values, let's say 1, 2, 4, and 5, and each with probability 1/4, okay? So the expected value of y is 1 times 1/4 plus 2 times 1/4 plus 3 times 1/4 plus 4 times 1/4, okay? And if you evaluate this here, if you evaluate this, you are gonna get, actually, sorry, let's actually say that it, yeah, 1 plus 2 plus 4 plus 5, sorry, here. So if you evaluate this, this is 1/4 times 1 plus 2 plus 4 plus 5, and this is 3. So these are two random variables, x and y, they have exactly the same expected value. But if you plot the distribution for x, so if this is, the distribution for x and the values that it takes, so this is p of x, here, x really just takes one value, and the probability of that is 1, so this is 1 here, right? So this is 3. If we look at the distribution of the values that y takes, we are saying that it takes the probability of 1. This is 1 here, and this is 2, and this is 4, and this is 5, and each one of them is 0.25. This is the probability of each one of the values that y takes. So if you look at these two random variables, yes, they have the same average, but they have very, very different distributions. The same thing when we look at the averages, for example, in a course, the average grade in a course, and we say that, let's say the average is 70. There are two huge differences between one case where every student is making a grade that's between, let's say, 68 and 72. These grades would average to around 70. But also you can have a distribution where the highest grade is 100 and the lowest grade is 30. And then you have enough grades of each that they will average to 70. So the average by itself sometimes might not be that meaningful, in the sense that it's a number that is not summarizing the distribution very well. And to distinguish between these two kind of distributions, for example, this is where we introduce the notion of variance, okay? So the notion of variance, in addition to the expected value of a random variable. So if you have a random variable x on sample space is, the variance of x, v of x, is basically, you can say that it's the sum over all possible values that x takes, and you take this x minus the expected value of x squared times p of x, okay? So let's look at it carefully here, what this is saying. This is simple. This is saying that the probability of every possible value that it might take, okay? So p of x here, let's say for the random variable we talked about here, in this case here, it's just the probability of 3, which is 1. But for these ones here, the x's can be 1, 2, 4, or 5, each with probability 0.25. But this is the more important one here. So if you look at this, x minus the expected value of x. Again, let me rewrite it here. This is the small x minus the expected value of the big X, okay? Remember that the big X is the random variable. E of big X is the average value. So X minus E of X, we are saying how far is this little x from the mean, okay? So X minus EX is how far it is from the mean. Now we take squared here so that the square achieves two things usually when you see a square in such a formula. The first one is that we turn every value into positive value, right? So if the mean is 3, we are saying that 2 from 3 and 4 from 3 have exactly the same distance from the mean. Okay, so we don't want to say 2 minus 3 is minus 1 and 4 minus 3 is 1. Both of them, we want them to contribute in the same way because they are far from the mean in the same amount of quantity. And the square, additional thing that comes from square, is that it amplifies big distances more. So if you think about, let's say E of x is 3 as we saw before. Let's look at one simple x to be, let's say, 3.1, and another little x that is, let's say, 10. If you look at this here, x minus E of x is 0.1. 0.1 squared is 0.01. Okay, so it's a very small distance from the mean. If you look at x equal 10 here, x minus the expected value of x, again we have 10 minus 3, it's 7, and 7 to the second is 49. Okay, so now it amplified. Not only we are saying that the x is 7 points away from the mean. No, we are saying it's 49 points away from the mean. So if the distance is larger, the impact or the effect under this square becomes even larger. Okay, so squaring x minus E of x achieves two goals. One of them is that it makes all these distances or all these differences positive. The second thing, which we could have achieved, for example, with the absolute value, but what square achieves over square absolute value is that it amplifies, it makes larger distances have much bigger effect on this. Okay, so this is the formula for the variance of variable x. But another formula that sometimes is easier to compute, and you can derive it from this, another formula is that the variance of x is the expected value of the squared random variable minus the square of the expected value. Okay. This formula and this are the same. Okay, they give the same value, but you can use either one of them. The first one, you can go after all the values that x can take. You compute the expected value, you subtract, square, and multiply by p of x. The second one is that you can compute these two expectations, one E of x and take it squared, and the other one is that you look at x squared and do the expectations. Let me just say something here about this E of x squared, because we have not seen it before, but this shouldn't be anything new. And what does it mean to have E of x squared? I remind you that E of x is the sum over all possible x's x of p of x. Okay, E of x squared is the sum over all x of x squared times p of x. Okay, it's not p of x squared, it's p of x. Okay, so this is what, and if we say, for example, if someone says what's the expected value of 3x to the 9, let's say, this is just 3 expected value of x to the 9, and this is 3 sum over every possible value x to the 9 times the probability of x. Okay, so this is just a function that you can apply. Okay, so let me just rewrite them here again to be cleaner. Is that the variance of x, one formula for that is that you sum over all possible values that it takes, and you take these small values minus the expected value of the random variable squared p of x, and you can derive from this that this is the same as computing the expected value of the squared of the random variables minus the square of the expected value. Okay, and both of them are useful in different cases, so you can use different ones in different cases. Okay, now one important thing is that we have seen that linearity of expectations, for example, and there we said if you have n random variables, then the expectation of the sum is the sum of the expectations. Now the question is that do we have the same thing for variance? The answer is unfortunately no. For the variance, we have to put an assumption on the random variables themselves for us to be able to use this linearity thing. So let me actually first say that we say that two random variables x and y, two random variables RVs x and y are independent if the probability of x equals x and y equals y is the probability of x equals x times the probability of y equals y. Okay, so if you look at x and y as two variables and look at every combination of values they take, if the joint probability of these values they take, x and y, equals to the product of the probabilities of the individual values, then they are independent. Okay, and when they are independent, one thing that it allows us is that if x and y are independent, then the expectation of the product of these two random variables is the product of the expectations. Okay, so again, this here is very important that x and y are independent, must be independent. Again, I remind you, when we looked at the linearity of expectations, independence did not make any difference. It was not part of the theorem there. Okay, and that's why linearity of expectation is such a convenient and powerful result. Once you write x as a sum of random variables, you don't even need to bother to check if these random variables are independent. However, if you want to go to the product of random variables, it's you cannot now take this formula for any two random variables. No, if the two random variables are independent, then you can say that the expected value of the product is the product of expected values. And when it comes to variance, now we have the linearity under the assumption of independence. So if we have x1, x2 all the way to xn are pairwise independent random variables, RVs, then what does this mean, pairwise independent? It means x1 and x2 are independent, x1, x3 are independent, and so on. Then the variance of the sum of these variables is the sum of the variances. Okay, but again, you have to have this assumption of independence, and this is very important. Okay, now if they are not independent, then not necessarily independent, then if I have x1, x2 all the way to xn, then the formula for the variance, the sum of the variance, the variance of the sums, the variance of the sums. Now, it is not just the sum of the variances. We have to correct it in some way here. So this becomes the sum as well as twice for I equal 1 to n, and for j greater than or equal to I here, time the covariance of xi and xj. Okay, what is the covariance of two random variables x and y? It is the expected value of xy minus expected value of x times the expected value of y. Again, when you look at these kind of formulas, please try to understand what they mean. If you look at this here, when we said, keep in mind that we said x and y are independent. We said x and y are independent if e of xy equals e of x times e of y. So if they are independent, what's the value of e of xy minus e of x, e of y? It is 0 if they are independent, right? If they are dependent, then the difference is not 0, and the difference is showing up here as in the covariance. So if you look at this, the value here is going to be how far from independence they are. So E of xy minus E of x, E of y is how far they are from independence, okay? And this is the covariance between two random variables, and we are summing over every pair of random variables. Notice here that the j being greater than I in the indexing of this summation is just saying that don't compute the covariance of x1, x2, and then the covariance of x2, x1. Again, the 2 is taking care of that in this case here, okay? So when we have a set of random variables x1 to xn, if they are independent, the variance of the sum is the sum of the variances. If they are not necessarily independent, then we have to take the covariance into the picture as well. And I want to just say here a few words at the end about this notion of variance, covariance, and so on, which we use sometimes in the area. You have seen them or you have heard of them in all sorts of areas. So again, let me remind you, v of x is the sum over all x's, x minus e of x squared p of x. One important notion that we talk about as well in statistics is standard deviation. Standard deviation is nothing but the square root of v of x. Okay, so this is the standard deviation. Okay, or STD of x. Okay. One important result about variance is that, as we said, for the sum of random variables, if they are independent, the variance of the sum is the sum of variances. But we have one important result about v of, if we take a constant times x, this becomes a squared times the variance. I remind you that e of ax is a of e of x. Notice that when the expectation, the constant stays the same, but in the variance, when you look at the constant, the variance of ax is a squared v of x. Okay, so keep this in mind here. Now again, these are not axioms. If you use the formula for v of ax, you should be able to derive that this is a squared x. Okay, and again, the other result is the notion of the variance of the sum of xi is the sum of the variance of xi if they are pairwise independent. And we have this is the sum of the variances plus twice the covariance of xi xj here, and we said that covariance of xi xj is the expected value of the product minus the product of the expected values. Okay, so the last thing I want to say about this is that this covariance has a good an interesting meaning and interesting use. So imagine, let me actually now illustrate this just with the covariance. Let's talk about x and y, and I'm going to visualize them. So suppose that we plot the values of these pairs, so x on the x-axis and y here. So for example, if x is 1, y is 1, I'm going to say, I'm going to put a point here. Okay, so this is 1, 1. So if some of the values that x and y take are 1 and 1, and suppose I continue to draw these values, they look like this. Okay, so these are the values. So if you look in the field of statistics or in the field of data analysis, you will see that very often we like to try to find some sort of a correlation between two parameters or two values. For example, I'm interested in looking at correlation between the height of an individual and, let's say, their cholesterol level, or the cholesterol level and their chance of getting a heart attack. Or I want to look at the correlation between the average grade of students and the the hardness of the measure they are in if I have some sort of measure of hardness. So if you look at these kind of points, and you look at, let's look at a different case here. This is x and y. So this is two different variables here. So suppose we have something like this. These are the values. And let's look at the third one, x and y. And these are the pairs of values they take. If you look at them and you ask a statistician or a data scientist to see if there is a pattern here, they will always tell you that, yes, they seem to be some sort of a linear correlation here. There's this linear correlation, and they will say there's a linear correlation. So if you look at this here in the first one case, the case here is that if you compute the covariance of x and y for these points here, you will see that it is greater than 0. If you look at, in this case here, you'll see that the covariance of x and y is smaller than 0. And if you look at the third one here, so the covariance of x, y, it's 0, basically. So the covariance of two random variables, that these two random variables correspond to some quantities of interest to us, you can use the covariance to measure correlation between these two variables, okay? So if you compute the covariance and it is greater than 0, then there is a linear positive correlation between x and y. If the covariance is smaller than 0, there is a negative linear correlation. If covariance is close to 0, then these two variables have actually the values have, there is no correlation between these two variables. So no matter what x is, y is still, the value of y is not really changing. So there is hardly any correlation there, okay? So the covariance, in addition to its being used in this formula for the variance of the sum of random variables, the covariance by itself for two variables is a very powerful quantity. In fact, the last thing I want to say that if you take the covariance of x and y and divide this by the standard deviation, so the standard deviation of x and the standard deviation of y, this is what we call rho, or the correlation coefficient, okay? So if you have two random variables and you compute their covariance, divide by the product of the standard deviations of these, you get the correlation coefficient. And one of the thing we know about this value is that it is between -1 and 1. So if you compute this rho and it's 1, then these two variables are perfectly correlated. If it is -1, they are perfectly inversely correlated. For example, as if x increases, y decreases at exactly the same rate. If rho is 0, there's absolutely no correlation between these, okay? So as you see, the covariance, it has its own use, and it's powerful in statistical data analysis and applications for computing correlations between two variables and so on. But the covariance itself also appears in the formula when we want to compute the variance of sum of random variables, because the variance of sum of random variables is the sum of variances only when the random variables are pairwise independent. When they are not independent, we have to add that covariances of every pair of random variables.